All right, good morning, everyone. So today we'll talk a couple loose ends. I won't be able to cover a couple of things I wanted to talk about. That's fine. It won't be relevant to the exam or any of that stuff. So that will be great. So yesterday we finished off by talking about, again, what keeps an object from infalling radially into the Earth, or the Earth radially infalling into the Sun, or etc., is because of its angular momentum, or because the fact that it actually has a linear velocity. So here, what we found was that the velocity that it has to have to keep it in a stable orbit is given by the square root of g times m, where this m is the mass of the central body, at which whatever it is it's orbiting, divided by r, where r is the center-to-center distance between the two. From there, we found the orbital kinetic energy, the orbital potential energy, and finally the orbital total energy, which is exactly equal to negative the orbital kinetic energy, or half of the potential energy. So let's use this and let's do an example. So what I have here is, this is a satellite. The satellite has a mass of 220 kilograms, and it's at an altitude where, again, I mentioned this yesterday, altitude is the distance from the surface of the Earth to where that satellite actually is, of 640 kilometers. And first thing we want to know is, when it's at the 640 kilometers, what then is the orbital velocity and the orbital period? So these are the two things that I want to know. Good. So from here, we know that the orbital velocity is simply given by g divided by, or gm divided by r. So, okay, so for Brian, we know that the orbital velocity initially is then equal to the square root of g, which again is Newton's gravitational constant, times the mass of the Earth in this case, divided by the radius, where the radius in this case would be the radius of the Earth plus the altitude. So here we know that the radius of the Earth is equal to 6.371 times 10 to the third meters. And we know that the mass of the Earth, so the mass of the Earth, I don't remember it offhand, kilograms. So the mass of the Earth is 5.9 times 10 to the 24th kilograms. And just remember, g is equal to 6.67 times 10 to the minus 11. So if we put in those numbers, what I find in this case then is that the orbital velocity works out to be about 7.54 times 10 to the third meters per second. So the satellite is moving with a tangential velocity of approximately 7.5 times 10 to the third meters per second. So that's pretty quick. So part B, the period, what we know is that what? 2 pi times the radius is equal to the velocity, which in this case would be the orbital velocity, times simply the period. So here, the period then is going to be equal to 2 pi, times again the radius of the Earth plus the altitude, divided by this orbital velocity. So this is our period. So plug my numbers, what I find in this case then is this has a period of 5.84 times 10 to the third seconds. So it takes roughly about 6,000 seconds for this thing to make a complete orbit. So not too bad. So next part then says, okay, let's assume that our satellite is actually low enough in the orbit that it feels some sort of friction force, so some sort of retarding force, and there's basically going to be something that's acting on it in this direction, which is causing it to lose energy at a rate of 1.4 times 10 to the fifth joules per revolution. So each time it goes around one circle, it loses 1.4 times 10 to the fifth joules per that revolution. So what we want to know is, if our satellite goes around the Earth then 1,500 times, from the initial conditions that we have here with this initial velocity and this initial altitude, what then will be the final altitude that it has, the final orbital velocity, and the final period after it has gone through 1,500 revolutions. So good. So how are we going to do that? Well, to do this, we're going to use this guy. So what we know is that initially this thing starts off with an initial orbital energy. So we know that the initial orbital energy in this case is then simply going to be equal to minus g times the mass of the Earth times the mass of the satellite divided by the initial height, which is then the radius of the Earth plus then the altitude. This is the initial energy at which it has. But then what we know is that each time it goes through one revolution, it loses this amount of energy. So we know then that what? At a later time, my erasers there. The energy then at some different time is then going to be equal to that initial orbital energy minus then the number of revolutions. So this is the orbital energy at some revolution n minus what I'm going to call this factor here, which I'm going to simply call the factor c. This is defined as c. Are we okay with this? So all I'm saying here is that at 0, or at the initial revolution, this thing has the initial energy. Then after 1,500, I'm then taking that as 1,500 times the rate at which it is losing energy per revolution. So this is going to have units of revolution to then find what is the energy at that particular revolution. Okay with this? Now, from here, what I know then is what? This guy then is going to have an energy of minus g times the mass of the Earth times the mass of the satellite divided by the new radius that this thing is at. And this must be equal then to the initial energy that it has, which is equal to minus g times the mass of the Earth times the mass of the satellite divided by the radius of the Earth plus the original altitude minus then n, where n in this case is 1,500, times the energy which is being lost, which is 1.4 times 10 to the 5th joules per revolution. So this has revolution, so this revolution will cancel out this revolution.
Where'd you get the R prime?
Oh, the R prime is just the new radius that I'm looking for. So this is the radius it has after 1,500 revolutions, which is different from this one. Or if I wrote it in terms of the new altitude, this would be the radius of the Earth plus the new altitude. Okay? Now everything here is a constant, everything here is a constant. This stuff up here is a constant. The only thing I'm looking for is h prime. So if I resolve this for then h prime, what I find then is that h prime works out to be about 6, oh wait a minute, sorry, 4.1 times 10 to the 5th. So that means it's roughly about 410 kilometers. So it has gone from an initial altitude of 640 kilometers down to a new altitude of 410 kilometers after it has gone through 1,500 revolutions. Okay? Good. Part B, we're now looking for what? The new orbital velocity. Well, again, find the new orbital velocity. Since we already now know h prime, we can then use that same exact expression over here, but now just take out h for h prime. So that means that for part D, my new orbital velocity then is going to be equal to the square root of g times the mass of the Earth divided by r prime. And it is the square root of g times the mass of the Earth divided by the radius of the Earth plus h prime. Again, plug in my numbers: 6.67 times 10 to the minus 11, 5.9 times 10 to the 24th. The radius plus h prime. This thing works out then to be about 7.67 times 10 to the 3rd meters per second. From here, I can then find the new period, which is then part B. So the new period, following what we did over here, the new period then t prime is going to be equal then to 2 pi times the radius, which is now the radius of the Earth plus the new altitude h prime, all divided by the new orbital speed, v orbital prime. plug in my numbers. What I find in this case then is it takes now about 5.6 times 10 to the third seconds to go through a full revolution. So only a difference of what? About 200 seconds. It's okay. So not too bad. Pretty straightforward. So one more thing to talk about to finish off this chapter. The last thing we want to talk about is orbital mechanics. So, for example, our solar system. So, turns out that our solar system comes down to describing the orbital mechanics, or basically how the planets all process around the sun, down to essentially 3 different rules. So these are what are known as Kepler's laws. We'll talk about Kepler's laws. So this is actually kind of an interesting story. So there was a Dutch nobleman by the name of Tycho Brahe, and he used to have his own private island, where he had his own private castle, where he had his own private telescope, and at night he would sit there and watch the stars and take rudimentary notes or ridiculously precise notes on exactly where all the stars were at every given moment of the night over decades. During the day, he would then test projectile motion by basically setting up catapults and shooting them at his cows and killing basically all of his cows. But he was a rich nobleman, so he didn't care. He would just buy new cows. So this is what he did. He had no way, or actually no intent on actually ever looking at the data. So he ended up hiring a postdoc by the name of Johannes Kepler to basically take his data and actually analyze his data. Shortly after that, Brahe died. Kepler then took it and then came up with these 3 laws of orbital mechanics. So what do the 3 laws say? So what the first law says is, number 1, that if this is the sun, then all planets orbit around the sun in an elliptical fashion. This is what the first law says. So all planets will orbit around the sun in an ellipse where the sun is at one focus of the ellipse and nothing is at the other focus. So this is the first law. So the first law says that all planets orbit around the sun with the sun at one focus and nothing at the other. So this is law number 1. Law number 2 then says, well, if my planet here orbits around in an elliptical fashion, turns out that if it starts off at here, let's call this point A, ends up here at point B, so that this thing sweeps out a area here, so let's call this the area going from A to B. At the same time, if it's way over here at this side, let's say it goes from this point here to C, to this point over here to D, so that way this thing sweeps out an area. So this entire area here is then the area from C to D. As long as the time frames are the same, so it takes this a time frame of delta t, and it takes this a time frame of also the same time of delta t, what the second law says then is that the amount of area which is swept out going from A to B in the time frame of delta t is exactly the same as the area which is swept out going from C to D in that same amount of time frame of delta t. So this is the law of equal areas. So the second law says that the area going from A to B is equal to the area going from C to D as long as delta t is constant. This is what the second law says. So it says that the area here swept out is exactly the same as the area swept out here, as long as those 2 time frames are exactly the same. So basically what this comes from is actually conservation of angular momentum. I'm not going to go through this derivation, but basically what you can show is that the time rate of change of this area here versus the time rate of change of this area here is equal to simply the angular momentum divided by twice the mass. So This thing is constant because angular momentum is constant because here there are no external torques because all the forces are pointing towards the center. Since they're pointing towards the center, which is only the gravitational force, it is then parallel to the radial vector which points outward, which means that there is no torque on the system. As long as there's no net torque on the system, angular momentum must be conserved, which means the rate of change here must be conserved as well. So this is simply equal to a constant. Okay? This is because there are no net torques. So angular momentum must be conserved. And this is the second law. So again, since angular momentum is conserved, what that means then is that this area here has to equal this area here as long as these two time vectors are the same. This is the second law. The third one, or the third law then says that the period at which it takes for the planet to orbit around the sun is directly proportional to the distance it is away from the sun. So the third law says that the period squared is proportional directly to the radius cubed. So this is what the third law says. So ultimately this says is that the period squared is equal to some constant k times the radius cubed. This is the third law. So if I want to know what this constant is, let's analyze it and try to figure out what this constant is. So let's say this is the mass of my sun here. This is, say, the Earth. We know the Earth is nearly in a circular orbit, so let's use the Earth as an example. So again, here what I know is that the gravitational force is pulling it towards the center of the sun. The centripetal acceleration must be towards the center, and this thing has some tangential velocity, which again is our orbital velocity moving in this direction. So, again, Newton's second law says that if I take this as my x-axis, the sum of the forces in the x direction must be equal to the mass times the centripetal acceleration, which again, the only force acting on it in this direction is the gravitational force. That must be then our centripetal acceleration. And using the definition of Fg, it says then that this is the gravitational constant times the mass of the sun times the mass of the Earth, which I'm just writing as little m, is then equal to the mass of the Earth times the centripetal acceleration. But since I want the period, it's better to use our third definition, which is then 4 pi squared times the radius, all divided by the period squared. And this side is divided by the radius squared. Since both terms have exactly the mass of the Earth, so I would then cancel out the mass of the Earth, and then solve this for the period. So finally what I get then is that the period squared is then equal to 4 times pi squared divided by g times the mass of the sun, all times the radius cubed. Which means that this constant k, the proportionality factor between the two, is then 4 pi squared divided by g times the mass of the sun. So this is my proportionality factor. So this is Kepler's third law. So Kepler's third law says that the period at which a planet will orbit around the sun is directly related to its radius by the fact that the period squared is proportional directly to the radius cubed, where this proportionality factor is simply the 4 pi squared divided by g times the mass of the sun. Now, this is not only true for a planet orbiting the sun, but this is also a true statement for any object orbiting another object. So just because it works for the sun doesn't mean it only works for the sun, it works for everything. Which means, for example, if I switch this out, instead as being the mass of the Earth, and this was then the mass of the moon, this would work as well. Which means the only thing that's going to be different in this expression, is instead of this being the mass of the sun, it's now the mass of the Earth. Or if this was Saturn, and then this was Titan, one of the moons around Saturn, this would work exactly the same way. And the only thing that would be a bit different is that this would be the mass of Saturn. So in general, this works for any type of astrological system where I have one object orbiting another object, where this is just the mass of the central body. So in general, we're just going to write this then as I squared divided by g times m, where again, this is the mass of the central body, then the radius of g. So this is something that's used in astronomy all the time. So if I see one object orbiting another object, and I measure the radius and I measure the period, I can then determine exactly what the mass of that central body is. For example, we use this all the time to figure out what are the masses of black holes. Black hole, by definition, you can't see. So what you'll see is, out in space with a telescope, you'll see a star which appears to be orbiting something in the center, but you can't see that body in the center because it's a black hole and it doesn't actually radiate away light. It does, but we just can't see it, but that's a whole other topic. That's quantum mechanics, but we won't get there. But let's say if I have the black hole here, this thing is orbiting, I have something in which it's orbiting, I can't see what it actually is, but I can now use this expression here by measuring the period and by measuring the distance it is away from that central body to then determine actually the mass of that central body. So from here, we can indirectly then measure the mass of something like a black hole. Or the mass of another star someplace else. Or pretty much anything that we want to, as long as it's orbiting something else. So this is something that's highly used all the time. So when it comes to Kepler's 3 laws, these 2 laws are more of ideas. This one is actually a mathematical expression, so this is something you would see on the exam. Hint, 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 wink, wink, wink. This one, or these 2, not so much. So again, these are just ideas, things that you have to know to get to that. But other than that, again, these are just more ideas and concepts. So this is orbital mechanics. So that's it, we're done. So let's now do a review for Monday's exam. Let's talk about Monday's exam. So Monday's exam, as you know, is going to cause or cover only 2 chapters. Even though one chapter seems like it's ridiculously long and the other one is not so much. So, but that's okay. So the first chapter we did was chapter 12. So again, chapter 12, what did we do? Well, we redid everything we had done up to that point, but now in things that were actually rotating instead of linear motion. So the first thing we looked at was kinetic energy. We said rotational kinetic energy is 1/2 the moment of inertia times the angular velocity squared. So this is rotational kinetic energy, where the moment of inertia is equal to the sum over I of MI/RI squared for discrete objects, which is also equal to the integral of R squared dm for continuous objects, where dm is equal to either lambda dl, sigma dA, or rho dV, depending on the geometry. So again, if I have a line geometry, or line symmetry, I have this one. If I have an area symmetry, I have this one. If I have a volume symmetry, I have this one. We also looked at rolling without slipping. Rolling without slipping, we said that the total kinetic energy is simply equal to the rotational kinetic energy about the center of mass, plus the translational kinetic energy of the center of mass, which then works out to be 1/2 times the moment of inertia about the center of mass divided by the radius of the object squared, plus the mass of the object, all times the center of mass velocity squared. So this is our total kinetic energy when it comes to rolling without slipping. Otherwise, we just have simply conservation of energy, which again says that the change in kinetic energy plus the change in potential energy must be equal to the work done by an oscillatory force. Again, here, this kinetic energy is going to depend on what the object is doing. So if it's rolling without slipping, it's this one. If it's simply an object like this, doing that, in that case, then it's simply this guy, 1/2 I don't make a square. It's not rolling without slipping, it's just rotating. Great. So that was that. After that, we then talked about torque. So torque, we said by definition is a vector which is equal to r cross f, where r again is a vector which points from the pivot point to the location of the force, and then f is the force itself. So if this was my object, this is my pivot point. Let's say I'm applying a force, I go down and say like this direction, this is the force. And r, again, is the vector which points from the pivot point to the actual location of the force. So this is r. Magnitude-wise, the magnitude of the torque is then equal to the magnitude of that vector times the magnitude of the force times sine of the angle between the two. So in this case, if I extend r in this direction, this is the angle between the two. From here, we can rewrite Newton's second law. Newton's second law then says that the sum of the torques acting on a system must be equal to the moment of inertia times the angular acceleration. Which again tells me that torque is the generator of angular acceleration. So why this thing here goes from what? A zero angular velocity down to something which doesn't have a zero angular velocity is because of the torque. In this case, the torque is acting on the center of mass of this object. There's a gravitational force pulling down. That's generating a torque, which is causing this thing to rotate. So the torque is what causes the angular acceleration. Just like force is what causes linear acceleration. Okay? So from there, the last thing we looked at then was angular momentum. Angular momentum says that for a point particle, the angular momentum is equal to r cross p. So again, this is for a point particle, which means the magnitude of the angular momentum is equal to r magnitude times the magnitude of the momentum times again sine of the angle between the two. So again, if I had some sort of coordinate system, this was my, say, z direction, x direction, y direction, and this was my particle of mass m, say, moving in this direction with velocity v, which means the momentum is in the same direction. And the vector r points from the origin to where that thing is pointing. So this is r. So again, if I extend r in this direction, again, that's the angle between the two. Okay.
Wait, what is R in there?
So r is vector which points from the origin of my coordinate system to the location of the particle. That's r. And then the momentum on here. So since the momentum is mass times velocity, it points in the same direction as the velocity, but it's either bigger than or smaller than depending on the size of the mass. Okay. So again, if I extend r, so this is my extension of r here, then the angle is the angle between those two things. So this is for a point particle. For a continuous object, or more importantly, what we call a rigid body. A rigid body is just simply something that does not deform under rotations. We have that the angular momentum is equal to the moment of inertia times the angular velocity. So this is what we call a continuous or a rigid body. So for example, this is a rigid body. As I rotate it, the object does not deform, it doesn't change shape. So this is what we call a rigid body. Unlike something like putty, where if I tried to do this, part of it would kind of flop down, it would deform as I try to rotate it. So that would be a continuous object, but not a rigid body. So we're not going to play with anything like that. We're only going to do rigid bodies. So something that does not deform under rotation. For both of these, what we can find then is that the time rate of change of the angular momentum is simply equal to the torque. From this, if the torque is equal to 0, this then tells me that my initial angular momentum must be equal to my final angular momentum. And this is conservation of angular momentum. One other thing we talked about briefly, I'll put it up here, is statics. So statics, we say that statics is the sum of the forces equal to 0 and the sum of the torques simultaneously be equal to 0. One more thing we talked about in chapter. Actually, this was not the first thing we did. First thing we did was the center of mass. Let me write that over here. So we also talked about center of mass. So we said that the center of mass, our center of mass, is equal to the sum over I of MI/RI divided by the total mass. And this is true for discrete objects. But if we have a continuous object, this thing turns into an integral. So in this case, our center of mass is equal to the integral over R vector dm divided by the total mass. And this is for a continuous object. So all this here is center of mass. Sorry, forgot about center of mass. Good. So that's all chapter 12. Chapter 13. So chapter 13, we talked about gravitation. So what we said is that we have two masses, M1 and M2, which are separated by a spatial distance of r. And the gravitational force between the two of those is equal to G times M1 times M2 all divided by r squared. So this is the magnitude of the force between the two of them, where this is an attractive force. If we have more than two particles, in that case we use the superposition principle. Superposition principle says that the net force on the ith particle is equal to the sum over the jth particles of then the force on I by j. So this is the superposition principle. All this means if I have a collection, this is the ith one, this gives me the first particle, second particle, third particle, doesn't matter. I have the sum over all the paired forces of these guys between all of them, vector sum them all together. So that's what we call the superposition principle. Again, this is only true for discrete masses. For continuous masses, in that case, I would have to integrate over the force. So in this case, this turns out to be Gm integral dm over r squared. So this is continuous objects. Oh, that hurt. Oh, that did that. Okay. Okay.
Is that on the top one, is that squared or just like M2?
That's M2. Yeah, M2. That's the mass of the second particle. Okay. What do we do about that? Potential energy, right? Is that where we went to next? Yeah, I think we did potential energy. Oh, sorry, Carson.
How do you go from df to the one under that?
Oh, so all I'm doing is I'm now using this definition here, where I'm saying that, so what's happening here is I have one little mass out here, M, versus another one that's chopped up into small little tiny pieces. So that little m here is what I'm calling M1, and I'm pulling that out. The second one then is all the different dimensional masses that I'm pulling inside of here. But since this is a constant, this is a constant, I'm pulling it outside of the integral, which means I'm left with the differential mass that I'm summing over divided by the distance r squared. So it's using this and this simultaneously. From here, we define now the new gravitational potential energy, which is equal to negative G times M1 times M2 divided by the distance r. From here, again, we can use conservation of energy, which says the change in kinetic energy plus the change in potential energy. For all of these problems will be equal to 0. The only thing that's going to be different here is that we're using the gravitational potential energy in this form. That's basically it. From here, we then did the stuff we started off with today. So we did for basically orbital mechanics. Orbital mechanics says is that the orbital velocity is equal to the square root of, so this was Gm divided by r. And here then is 2 pi r divided by the orbital velocity. So this would be for like a satellite or a moon or something like that. And finally, we have Kepler's third law, which says that period squared is equal to 4 pi squared divided by gm times the radius cubed. So let's go to Kepler's third law. And that's it. What's up, Kristen?
I noticed on the problems we were using earlier, sometimes R would equal R plus A. Should we just go?
Correct. So it just depends on what I give you. So I'm either going to give you the distance from the center to where the object is, or I'm going to tell you its altitude, which is then the height above the object itself. So, good. So let's draw that over here. So basically, just the difference is, over here. So this is my central body. This is where the mass is orbiting. Remember, R is the total distance from the center of the one body to the other body. Or if I say this body here has a radius of capital R, and this thing is some height h above that, then R is equal to the radius plus the altitude.
Okay.
Both of them mean the same thing. So it just means the total distance from the center to center. Yes. Yes. So let's talk about all the things I will give you. That's a good question. So things I will give you, let's go back to here. I will give you moments of inertia of an object about its center of mass. But if the pivot point is not about the center of mass, something else you want to write down then is called the parallel axis theorem. We used. What the parallel axis theorem says is that this is the pivot point I want, this is the pivot point I'm given, which is the center of mass. The moment of inertia about that pivot point is related to the moment of inertia about the center of mass, plus the mass of the object times the distance I am away from the pivot point to the center of mass squared. So this is our parallel axis theorem. So things I will give you are exactly that. I'll give you moments of inertia for different objects about the center of mass. If the actual pivot point is not about the center of mass, I'll expect you then to use the parallel axis theorem to move it where it's supposed to be. Good. So that's the things I will give you. Other things I'll give you are basically pretty much all the constants. So basically, G I will give you if I have a mass of like the sun or the earth, something like that, I'll give you that. I'll also give you the radius of the earth. So any of those types of constants.
What's M on that?
So M is just the mass of this object. Whatever that object happens to be. Yeah, so all those I'll actually give you. So one thing I should know about the next exam, which will actually be your final exam, but half of that will be based off the new material. That is loaded with constants, which basically means you'll have about 2 pages worth of constants for that exam. Which is a whole bunch of constants. You'll see that as we actually go through all the stuff. So there we'll be talking about heat flow indexes and all kinds of different stuff. And so there's just a constant for every different type of material, specific heats, all kinds of different stuff. So there'll be a ton of constants in those cases. This one's not too bad. Only a few constants. Okay? So let's talk about what types of problems we should expect. So there wouldn't be one long problem here. So basically using these ideas of gravitation, there'll be one long problem. I believe there'll actually be a short answer from here as well. One short calculation from this as well. So for example, the short answer one might be, I'll give you a whole bunch of point particles in some arrangement. You have to find the force on one of them. Kind of like what we did in class, where the one we did in class was the square. We had 4 masses, and then we put a 5th one in the center, and we said, what was the force on that 5th one in the center? So that would be like a short answer proof calculation problem, something like that. Good. Let's see here. So there will be one problem, a long problem, which involves this. basically conservation of angular momentum with conservation of energy. Similar to what we did on the last exam. So here, you want to concentrate mostly on collisions. Remember your three different types of collisions. You have elastic, inelastic, and perfectly or completely inelastic collision. So basically, something's going to stick to something else, or it's going to penetrate through it and keep going, things like that. So we did an example like that in class. So you'll have to use conservation of energy and conservation of angular momentum. So that'll be one long problem. So that's 2 so far. So not too bad. The third one then will be mostly involving torque and forces and finding accelerations and all that good stuff with something which is rotating. So again, we did a bunch of examples like this in class, but a good example of this would be the Atlas machine. So for example, we had Atlas machine attached to 2 masses, M1, another one attached over here to M2. We found what was the acceleration of this guy, with how this guy was rotating with an angular acceleration. So here we have to do a combination of both Newton's second law for linear motion, Newton's second law for rotational motion, some of the forces, some of the torques, all that kind of good stuff. So, all kinds of different things. Inside of there, of course, will be buried things like moments of inertia and all that kind of good stuff. I think I should say is obviously attached to here is this. But anywho, so that's all 3 long problems. Other short ones will be other stuff. So again, conservation of angular momentum, kind of stuff like that. Rolling without slipping, all that kind of good stuff. So having said things like that, calc pointers, you guys are not quite in integrals yet. Am I correct about that? I think so. Which means that integration, at least on the main portion of the exam, is off limits. So there will be no integration on the regular portion of the exam. Doesn't mean it won't show up in the extra credit. But in the regular portion, it will not be there. Derivatives can be on there. You guys have already done derivatives. We did that in the last exam, so derivatives could be there. Those are viable, but integrals will not be part of the regular portion of this exam. Okay? Any questions on this stuff? So like I said, it's the same stuff we've done before. So one other thing I'll have you write on your equation cards, just to remember, is remember our replacement rules. So hopefully you can remember those. Remember that x goes to theta, b goes to omega, a goes to alpha, m goes to I, f goes to tau, and finally p goes to L. Remember, these are replacement rules. If you don't remember any of the angular portions or the linear portions, just make those replacements in the appropriate one, and then you get exactly the correct statement back. So again, kinetic energy, for example, if I wanted the translational kinetic energy, I just replace I with m, omega with b, so I get 1/2 mv squared instead of 1/2 I omega squared. So these are our replacement rules. And that's about it. It was okay? So I got one more group assignment for you. Let's get started on that. At least we'll talk about it. This has to do with gravitation. So this one is mostly talking about what's called the spaghetti effect when it comes to black holes. So basically what happens with black holes is you have this big, massive object, by its definition, has an infinite mass density at a single point in space. This is how we actually define a black hole. From there, you have other things that are called the event horizons, which is what this is called. The event horizon for what's known as Schwarzschild black hole is given by 2gm divided by the square root, c squared. What basically happens is the gravitational forces around the black hole are so great, these are called tidal forces, that if I was falling into the black hole, my feet would feel a much greater force than my head if I was falling into the black hole feet first. Which basically means that what would happen is your feet are being pulled into the black hole harder than your head is being pulled into the black hole, which means you would actually be stretched. This is what it's called the spaghetti effect. So you're taking an object and stretching the hell out of it until eventually you're going to rip it apart. So what this problem is basically asking you to do is to look at, you're at some radial distance of 50 short-tailed radii away from the center of the black hole. And what it basically says is that you can withstand a difference in acceleration between your feet and your head of up to roughly about the acceleration due to gravity. So 10 meters per second squared. So what it wants you to do then is use what we know about gravitation then to figure out what then is the limit of the mass of the black hole that you then wouldn't be pulled apart. So that the spaghetti effect wouldn't be enough to basically rip your toes off, rip your feet off, rip your ankles off, your knees, etc. So not actually physically rip you apart. Because we can withstand that. Anything greater than that, we're going to be pulled apart. So what this is asking you to do then is find what is the limit on the mass of the black hole that will allow you to safely fall in. Now there's other ways you're going to die, but we'll talk about that later. Then the next part wants you to find out, is this a upper limit or a lower limit? Meaning that the limit of the mass that I find, if I go below that mass, is it going to pull me apart? Or if I go above that mass, is it going to pull me apart? So it wants to know, is it an upper limit or a lower limit? Meaning if it was an upper limit, if I went below that mass, I'd be fine. It's called an upper limit. Or is it a lower limit, meaning if I went above that, I would also be fine. But if I went below that, I'd be pulled apart. The answer is, I'll tell you this now, is it's actually a lower limit. Turns out with black holes, the bigger the black hole is and the more massive it has, the lower the tidal forces, which basically means you have a higher chance of probability of surviving with a more massive black hole than you do with a smaller black hole. Smaller black hole, the tidal forces or the gradient between those forces is much, much greater. Means you would actually die a much horrible, more death going into a microscopic black hole than you would into a huge, supermassive black hole like the one in the center of our galaxy. Now, other ways you would die, of course, is that black holes, as I kind of mentioned this earlier, actually do radiate. It's a quantum mechanical effect, which actually means that the temperature around the black hole is approaching infinite temperature, which means you would actually burn to death and die ever before it would actually rip you apart, which is actually kind of cool. But anyways, so, and then if you actually made it in, so the radiation wasn't enough to kill you, you would die because you'd be crushed to death by space and time itself because I have an infinite density at a single point in space. So you basically become part of space-time and you would die. So, much like we talked about yesterday, a lot of ways to die, but that's great. So okay, that's all this wants you to do. So go through this, try to find this limits of the mass of the black hole. Once you find that limit, tell me is it an upper limit or a lower limit, and basically why. And as I told you, it's actually a lower limit. So you just gotta tell me why. Well, that's it. Everybody have a great holiday weekend. Thank you very much. See you later, Kristen. What's up?
You received the email I sent.